In the previous videos, we have looked at the relative stability of anions. So here I have sort of summarized different series. So in series 1, 2, 3, 4, 5, we have already looked at how we will predict the relative stabilities of these anions within this series. So in this series, notice that the negative charge is on different atoms and the atoms are in the same row. All these atoms are in the second row of the periodic table. So that is one set. So here we have utilized the electronegativity of the atom on which carries the negative charge. So fluorine is the most electronegative, so the fluoride ion is the most stable. So we have dedicated one video for that. And in the next example, in the next series, the negative charge is on the same atom, oxygen and oxygen. So here we cannot use the electronegativity of oxygen because it doesn't really help us in any way, but we focus elsewhere. Notice the extra fluorine here. There's no fluorines, and you know fluorine is an electronegative element. It pulls electrons towards itself because it's highly electronegative. So this negative charge sort of gets pulled over all these atoms towards fluorine. So the negative charge is stabilized, and we call this a negative inductive effect. The electrons on this oxygen atom are being induced away from that oxygen, thereby stabilizing that negative charge. There is no such thing happening in this ion, in the left CH3O minus, so it's less stable ion compared to the other one, compared to the one with fluorine on it. Okay? So another video for that. And here we looked at a different set of ions, negatively charged ions. Again, the negative charge is on the same atom, oxygen versus oxygen. So again, you cannot use electronegativity, but if you look at these two, there is a possibility of resonance here. We talked about resonance in one of the previous videos. So the negative charge is stabilized by resonance here. So different situations, different explanations. Okay. So we need to learn all these things to move ahead in the course. And in the fourth series, I have put only a couple of examples there: iodide and bromide, just two of them. You can also think about chloride and fluoride. Here, what do you notice? Different atoms, iodine, bromine, the negative charge is there, so iodide, bromide. But what do you notice there? Those atoms are in different rows, or periods. So you have fluorine in the second row, chlorine in the third row, bromine in the fourth row, iodine in the fifth row. So fifth, so in the periodic table. So as the periods increase, as the atomic number increases and the atomic size increases, so there we used size to explain the stability. So iodide ion is much larger than the bromide ion because it has that extra shell. So the electrons have much more room to spread out and be stabilized. So we invoke a different one. Now we come to the fifth set. Here the negative charge is on carbon. Three examples, three different ions. The negative charge is in the carbon in each of these cases. But what's the difference? The difference is this carbon is connected to the other carbon by a single bond, this carbon by a double bond, and this carbon by a triple bond. So now here we invoke a new concept for us, which is called hybridization. I'll just write that here and then we'll talk about that. Hybridization, since I don't have space, I'm just writing that here. Hybridization. Okay, and we'll introduce why the concept of hybridization came up and all that. It'll take 1 or 2 videos because we're keeping the videos to short amount of time. So let me erase this and then I'll come back to make a next video focusing on hybridization.